Welcome to this explainer. Okay, I want you to picture the ocean for just a second. It's this vast, rolling reservoir of immense, completely untapped, clean energy. I mean, we're talking about the ocean holding enough kinetic energy to literally power the entire globe several times over. It's power that could theoretically light up entire coastlines and just completely transform how we run our world. But actually capturing all that kinetic energy, yeah, that's historically been one of the great engineering puzzles of our time. So today, we're exploring a seriously fascinating theoretical breakthrough in fluid mechanics that might just hold the key to taming all that ocean chaos. Let's get into it.
Because right now, we have this fundamental clash at the heart of the puzzle. It's the chaotic, raw power of the ocean versus our desperate need for consistent, reliable, clean energy. You see, the ocean obviously holds a massive amount of energy, but it is wildly unpredictable. Waves are constantly changing their force, their height, their direction, literally from minute to minute. And this constant variability has made it historically incredibly difficult to harness that energy consistently enough to actually make it a practical power source for our electrical grids. Which is exactly why scientists are now modeling a fascinating technological solution to solve this specific variability problem.
Section 1. Enter the gyroscope. So, the core concept here is something called a GWC, or a Gyroscopic Wave Energy Converter. And it's actually beautifully simple, even if the math behind it is, well, incredibly complex. Let's break that down so we don't get lost in the acronyms here. Simply put, a GWC is a floating body that just sits right there on the surface of the water. Inside this floating shell is a spinning flywheel, and that really heavy flywheel is connected directly to a generator.
Okay, let's walk through the mechanics step by step. It's this incredibly elegant chain of events. First, the unpredictable ocean waves toss and turn that floating body on the surface. Second, all that violent tossing and turning forces the internal flywheel to spin and tilt within its housing. And third, as that flywheel spins, it drives the connected generator, which ultimately produces electricity. It's a mechanical translation, taking chaotic physical wave motion, turning it into mechanical spin, and outputting clean electrical power.
Now, if the ocean actually offered the steady, perfectly predictable ideal waves that you see in theoretical models, well, early GWECs would have been a massive success a long time ago. But, as we all know, the reality is a chaotic mess of constantly changing force and direction. Because of this extreme day-to-day variability, previous GWEC devices really struggled to reach any practical levels of efficiency. They just couldn't handle the ocean's physical mood swings.
Section 2. Iida's Breakthrough Model.
This brings us to a new study published in the Journal of Fluid Mechanics by Takahito Iida from Osaka University, and it presents an absolute paradigm shift. Iida notes that while wave energy devices struggle with changing conditions, quote, a gyroscopic system can be controlled in a way that maintains high energy absorption, even as wave frequencies vary. This is huge! We aren't just letting the ocean randomly throw our device around anymore. No, we are actively controlling the system from the inside to perfectly adapt to the chaos outside.
So, how do we actually exert that kind of control? Well, the secret ingredient here is linear wave theory. This is a powerful mathematical model used to calculate the incredibly complex interactions between the rolling ocean waves, the internal spinning gyroscope, and the floating structure itself. Because remember, the ocean isn't just pushing the float is actually pushing back, and the spinning mass inside is reacting to all of it. By using the advanced mathematics of linear wave theory, Iida was able to calculate the absolute optimum setup configuration for the entire machine.
To really understand how this optimum setup works in practice, we have to talk about precession. Precession is simply the way outside forces nudge a spinning object. Think of a spinning top on a table that starts to wobble when you tap it. That specific wobble? That's precession. By fine-tuning the rotational speed of the flywheel and the resistance of the generator, the GWEC system can actually adjust its own precession on the fly. It's a lot like continuously tuning a radio dial to keep a clear audio signal, or a sailor constantly adjusting their sails to catch a changing wind. The flywheel actively adjusts its wobble to gracefully match whatever frequency the ocean is throwing at it.
Section 3. Unlocking 50% efficiency. When you combine that active, dynamic tuning with the heavy math of linear wave theory, you hit the climax of this breakthrough. 50%. By actively fine-tuning the spinning flywheel's rotational speed and the generator's internal resistance to perfectly match the wave conditions outside, Iida's mathematical modeling shows these devices can theoretically hit a maximum of 50% efficiency. That means converting up to half of a given wave's total kinetic energy directly into usable electricity. And guys, in the complex world of wave energy theory, 50% is widely considered a fundamental constraint. It's a sort of strict theoretical ceiling for energy capture, and this mathematical model actually hits it. But honestly, hitting that ceiling isn't even the most impressive part here. Iida points out that this efficiency, quote, can be reached across broadband frequencies, not just at a single resonant condition. Those two words, broadband frequencies, are the absolutely crucial takeaway. It means this incredibly high efficiency isn't just some parlor trick for perfect laboratory-controlled waves humming at a single frequency. The gyroscope can theoretically maintain that high efficiency across a wide band of chaotic, day-to-day oceanic variability. It literally handles the chaos.
Section 4. Limitations and future tests.
Now, let's do a quick reality check. Because science isn't magic, and theoretical computer simulations always have their boundaries. The current study definitely has a few key limitations we need to keep in mind. First, while the computer simulations backed up the math perfectly, they still relied heavily on mostly idealized wave conditions, and waves are just notoriously hard to simulate with absolute perfection. Second, when Iida modeled the gyroscope in highly lopsided and uneven waves, more like a stormy real-world ocean, the efficiency did drop, though it still managed to extract a decent amount of power. And third, these theoretical calculations currently exclude the actual power cost required to actively run the gyroscope's digital controls out on the water. So this is very much a brilliant first step in proving the math rather than a final finished product.
But man, what a first step it is! Let's look at the horizon here. The next steps outlined by the researchers are incredibly exciting, and they're already being planned. We are officially moving from the computer screen to the water, with real-world physical model tests to validate this fluid mechanics theory. On top of that, Iida notes that if we move away from symmetrical floating bodies and begin to really explore asymmetrical designs, we might actually be able to break past that 50% efficiency ceiling entirely. We are truly looking at a future where entire fleets of these floating gyroscopes, actively tuning themselves and dancing with the changing tides, could make a massive contribution to our planet's green energy balance, which leaves us with this final provocative thought to ponder. Is the key to our green energy future already spinning in the ocean? I want you to think about that the next time you look out at the crashing waves. Thank you so much for joining me for this explainer. I hope this really helped clear up the incredible mechanics behind wave energy. Keep wondering, keep learning, and I'll catch you next time.